Very good morning to all of you. At the outset, I would like to welcome all of you to this lecture. Before I proceed into this lecture, I would like to first introduce myself as Shanmugavel, Professor of Electronics and Communication Engineering, and I have some 30 years of experience in this field. I have been teaching communication subjects and related subjects all through my life, and spread spectrum technique happens to be one of my pet subjects, in which I have carried out some amount of research in this field, and as a part of advanced communication system, I am very happy to share my experience with you in this subject. So in fact, in this subject, you must have learned other techniques of digital communication, such as representing analog signal into digital form, and then it's generally called source coding, which is converting a waveform into binary digits, and then baseband communication, and then bandpass communication, like modulation, in which you must have learned spread spectrum. You must have learned BPSK, BFSK, QPSK, and MLPSK. So these are various modulation schemes using which you transmit signals in order to use the channel efficiently. So in this process, you must have understood that in communication, you must have selected certain signals for transmission in keeping in mind the channel conditions, and you must have been taught about the performance of these techniques in presence of certain channel impairments, particularly noise. So when you transmit signal from one place to another, in between there is channel. Channel could be a guided medium or an unguided medium. It could be a coaxial cable, fiber optic cable, or a free space medium. So this medium can introduce any type of impairment on the transmitted signal. So the corrupted impaired signal only is received at the input of the receiver, and using certain processing techniques in the receiver, the effect of such impairments is greatly reduced, and then a signal is delivered to the user. So signal means a quality. You should deliver a acceptable quality signal, for which quantitatively speaking, if it is an analog communication system, they say a signal to noise ratio of 40 dB or so, or if it is digital communication, a bit error probability of less than 10 power minus 5 is to be delivered at the output. So as far as the channel is concerned, only white noise might have been considered, additive white Gaussian channel. So channel must have been modeled as additive channel, white noise channel, Gaussian channel, and corresponding time domain waveform would have been assumed in order to analyze the performance of these techniques. So I'm sure you would have understood what is white noise, what is Gaussian noise. So white noise means the noise has all frequencies extending over the complete frequency spectrum, like the white light. So it influences the transmitted signal in all the spectrum. Wherever, in whichever is the bandwidth you are transmitting, there is going to be noise. So that is the assumption. And Gaussian noise means the amplitude of the noise that is generated in the channel has a Gaussian distribution. It is random in nature, so random signal cannot be mathematically expressed as a particular waveform. So it can be quantified using in a probabilistic domain. So that is normally assumed to be Gaussian in nature, in which the probability of noise voltage being around 0 is very high, and probability of noise voltage being higher and higher voltage is going on reducing in the form of a Gaussian spectrum, Gaussian PDF. So, and otherwise, this noise also is said to be thermal noise. This noise is produced due to one in the atmosphere and other in the system itself. So, due to the temperature of the system at which the system is operated, the noise is produced accordingly. So, it is also called thermal noise. So, thermal noise is modeled in the frequency domain as white, in the amplitude domain as the Gaussian noise. So, using this model, you must have been taught how any modulation scheme performs in presence of this noise alone. But unfortunately, the channel introduces very many interferences which could be unintentional or intentional, or there are so many other unwanted operations that will take place in this channel, which have to be dealt with. So, for example, noise is a natural phenomenon. Nobody intentionally introduces noise. But suppose somebody intentionally generates a noise and transmits in the band of your interest, or somebody introduces intentionally some other waveform to collide with your waveform in the transmission, then in that case, the conventional modulation schemes cannot detect such interferences and cannot provide you with the required quality of reception. So you need special techniques in communication in order to deal with such impairments. So there is one such technique called spread spectrum technique, in which what is normally done is the spectrum of the original signal is spread over a large duration. For example, considering the digital communication, the signal that you normally transmit will be binary digits. So binary digits will 1, 1, 1, 0, 0, something like this. Correspondingly, there is a waveform. There is a waveform like this. Okay, 1, another 1, and then a 0, 0, and 1, 0. Like this it goes. So this is the waveform that you will transmit. So this is to be modulated onto a carrier. So if you modulate onto a carrier, suppose BPSK, what happens? Correspondingly, there is a waveform. So I'm just something like this. Okay, for each bit there is one. So you will select a particular. This is a carrier frequency, and this will repeat. And when one becomes 0, so you will correspondingly phase will change, and 0 becomes 1, the phase will change. So I'm not exactly, it is not to a scale, but to show you that there is a phase change here, there is a phase change here, and phase change here, I am drawing. So such a waveform you will transmit. This is the time domain. This is time domain. This is time. Equivalently, in the frequency domain, if you look at these waveforms, so the spectrum is F. So corresponding to this, you will find, I'm drawing a power spectrum, okay? Suppose I call this as S of t, and this is X of t, and this, let us say, S of F, power spectrum. It will have a spectrum of something like this. For example, it will be like this. Like that it will go. Okay, this is 0, and this will be say W. I call this a W, where W is equal to 1 by TB. TB is the bit duration. This is TB. 1 bit duration is TB. So this will go like this. To modulate with the carrier frequency FC equal to some much greater than, so bit rate, much greater than RB, which is called a bit rate. So bit rate RB equal to 1 by TB. Okay. So this carrier frequency is chosen to be much greater than RB. So this corresponding spectrum, so it is around RB. So this is FC. So the same spectrum is shifted like this, like that, like that, like that, and so on. Similarly, minus FC, like that, like that, like that. So this is how it will be. Same will be shifted. So this is how the spectrum of the original transmitted signal will look like. So let us consider. This type of communication, if you straight away transmit this type of waveform, is called baseband communication, which you would have already learned. So baseband spectrum is like this. If you modulate and transmit, it is called band pass communication. The band pass spectrum is like this. So when you want to transmit a baseband signal, you need to provide a bandwidth of W. When you want to provide, when you want to transmit using band pass signal, then this bandwidth is equal to, depending upon the modulation scheme, this will vary. If it is BPSK, it is 2 times W. Okay, so if for BPSK scheme, that let's see. Oh, sorry. So for BPSK, it is 2 times. So there is, this is the RF bandwidth, this is the baseband bandwidth. This is B, in this case, B is equal to W, here B is equal to 2W. So for the sake of explaining the spread spectrum technique, I will consider a baseband communication so that it is easy for us to understand the technique. And I also would assume that if you look at the spectrum, it goes to infinite like this, because this is a square wave. Square wave will have infinite frequencies, but the frequencies, higher frequencies will have a lower and lower strength. So this is called main lobe. Okay, main lobe here. So these are called side lobes. It can be shown that the main lobe contains more than 95% of the total power, total energy for the second. So majority of the energy is in this band. So we can approximately consider the bandwidth of this signal to be this W. Okay, this is minus W. So spectrum is W. Here also approximately you can consider this bandwidth to be 2W. We delete the side bands. So if you provide 2W bandwidth, it is sufficient for a BPSK signal to go through your channel and come out as it is, okay, without much of distortion. So I would consider that the baseband spectrum to be like this. So baseband communication, I assume. Okay. So the baseband spectrum will be something like this. So I consider this spectrum like this. This is the spectrum S of F. Okay, this is W. This is minus W. And now I transmit this waveform. In the channel we have a bandwidth W. So this waveform will go into that channel and come out with slight distortion, but that distortion can be handled easily. So come out this waveform will come out. If there is noise, so in presence of noise, if the noise power is such that signal to noise ratio is around 40 dB or more, then required quality can be delivered, as you already learned in other classes. Now the question is, let us assume that noise is always present, but in addition to that, there could be other interferences, which could be intentional or unintentional. If you have to tackle these interferences, what they have said is, instead of this is the original spectrum of the signal, and you convert this into, so this is F, this is the spread, I call it a spread spectrum signal. So it is something like this. They convert this into like this. Okay. So this area and this area are the same. The whole energy in this band is dispersed into like this. This is that as a WS spread spectrum, WSS. This is minus WSS, where WSS is much greater than W. So how many times greater? That is for us to decide. So this spectrum is spread over a large bandwidth, but same energy. Okay, if this is the particular highest value is 1, this may be 0.2 or whatever it is, but it is spread over a large bandwidth. If you spread it and then transmit, it has got the capability to reject the unwanted intentional jamming or intentional any other activity. So this is what is called a spread spectrum. You spread the original spectrum using some technique, using certain method, you spread it, and this has got the potential to reject the intentional interference like jamming, and unintentional interference like multiple access interference is one such thing, and then low probability of intercept. That means when somebody wants to this is what normally happens in military communication. In the civilian communication, no one will intentionally jam your signal, because you are not allowed to jam. If anybody is found to be jamming the signal, then they will be taken out of the system. So intentionally no one will jam, but there could be unintentional jamming, unintentional interference because of the multiple access system, which maybe you will learn later. I'll come to it later. Multiple access. But in military communication, the enemy would like to intentionally jam your signal. So how does it jam? It will generate some other garbage waveform in your band of interest. You are transmitting in this band. For example, in a particular band like this band. In that band itself, they will generate. You are transmitting this waveform, but they will transmit some other garbage waveform in the same band, so that it will interfere, and you will not be able to detect your original signal. But if you spread the bandwidth like this, and in this band, if somebody intentionally generates another waveform and puts into this band, it is possible to get back this original this band and reduce the effect of this jamming signal to a great extent. That is what is possible. So how is it possible? We will come to later. So what I am trying to explain to you is that in the channel, channel impairments, so there could be noise, which you already learned. Noise is one thing. Intentional jamming, okay. Multipath interference, okay. Multipath, multiple access interference, okay. Multiple access interference. And then intercept, signal intercept, whatever it is, signal intercept. All these things could happen. If this noise is some waveform, randomly generated waveform, will be added to your signal, and in presence of noise, how to get back the signal, you have learned already. Now this jamming. Jamming is also an electrical signal using which your signal is jammed, and there could be different forms of jamming. The jammer could generate a waveform, any type of waveform to jam your signal. They can generate a noise-like waveform, jam it, noise jamming, or they can generate narrowband noise signal, jam it, or they may generate pulse jamming. That means they will not jam continuously throughout the time. They will jam only specific instances, and then jam your signal. That is another technique. And they could also jam by transmitting tones. Okay, particular frequency in your band of interest with high power. They will jam and then create problems. Depending upon whatever technique you use, they will also accordingly change their jamming strategy. So in presence of all these kinds of jamming, one has to survive. So this is a question of survival of communication. So this is very important. So this is what you learn. If somebody jams your signal, how do you successfully communicate is the question. For which this technique, spread spectrum technique, will help in reducing the effect of jamming. It cannot avoid, completely eliminate the effect, but it can reduce to a large extent so that a successful communication can be had. Okay, that is one thing. Then multipath and multiple access interface. This is the one, that when there is a resource available, particularly in our case, always it is a bandwidth. The bandwidth, the same bandwidth will be shared by many people. Okay, because one particular user will not be normally one particular user will not always use the bandwidth. So if it is not used, is unused, then it is a wastage of resource. Therefore, there is what is known as a multiple access. Same resource will be accessed by multiple users simultaneously without one interfering with the other. So there are many techniques. In time domain, you can provide. Frequency domain, you can provide. There is another domain called code domain, which is basically spread spectrum. So there are multiple access techniques, which is a cooperative communication system. Multiple users will cooperate among themselves to transmit in a different frequency bands so that one will not interfere with the other, or different time slots so that one will not interfere with the other. Similarly, different codes they will use without one not interfering with the other. So there are many techniques. In that case also, what happens is unintentionally, one band will interfere with another band for various reasons. We will not have time until now, but later on. So there can be unintentional interference. Such interferences have to be also eliminated, and you have to survive the communication. These are unintentional. So that is one thing. This technique will help you even survive in such unintentional interference also. And intercept. This will provide low probability of intercept. Actually, when your signal you are transmitting in a particular environment, enemy may try to intercept your signal. That means they will hear the signal. They'll also know how to track your signal. When you are transmitting your signal in one particular band, they will also know how to track where in which band you are transmitting. They will detect that signal and then try to make meaning out of it. So they will have to know at what frequency you are transmitting, and what is the bandwidth of the signal, what is the technique you have used to modulation technique you have used, or a coding technique that you have used. All these things they will come to know, and then they will know what is the message that you are sending. Now, we need a technique that, in spite of them getting this signal with them, they will not be able to make any meaning out of it. So the spread spectrum technique will make such interceptors very difficult to make meaning out of it, because after spreading the signal, if you look at the waveform, it will almost look like noise. So the interceptors will not be able to make meaning out of that noise. But the intentional users, now we are trying to transmit to some particular user. That user will know how to make meaning out of such a small noise-like signal, because they know, the intended user knows how we have spread the signal, and they will use the same technique to de-spread it and get the message. Whereas the enemy will not know what is the technique or what is the code that we have used to spread the spectrum, so that the probability of intercept will be very, very low. So they cannot easily intercept the signal and make meaning out of it. So we can survive without any danger. So for which we need that. So mainly noise is unintentional, which we already learned. This is also unintentional, but still it requires certain specific techniques to reduce the effect of unintentional interference. Spread spectrum will help you. Jamming is intentional, military type of communication experiences this kind of jamming aspect. And intercept is also in military. These two are in military communication. So how this spread spectrum technique helps in reducing this effect of this kind of impairments is the question. So what we have so far tried to understand is that normally we have a digital information, and if the channel is only noise is in the channel, if there is only noise present, AWGN, then we can simply modulate the original signal using a modulation technique and receive it and provide acceptable quality of signal. But in the channel, apart from noise, if there are other interferences like intentional, unintentional, and other impairments, then we need a special technique in order to survive in such an environment. And spread spectrum happens to be one such technique. So spread spectrum means you are spreading the original spectrum into a large spectrum, so that these impairments can be easily rejected, or can be effect can be largely reduced. So the question is how to spread the spectrum, and what are the techniques to spread the spectrum, etc. is a question here. So how much of spread one has to have? It depends upon how much of jamming or how much of interference that one experiences. So that has to be decided by seeing the environment in which we are operating. So that will be that is called a gain, processing gain one has to provide in this perspective. So now let's see how to spread spectrum. Now, as I told you, we had a binary waveform. It had a particular spectrum, and if it has to be spread, it is related to now. Let us say like this: suppose binary waveform. Is 1, 1, 0. Okay, data. This is the data, original data. And in this case, the bit duration is, this is the bit duration, TB, one bit duration, another TB, and so on. So the spectrum here, this is time domain, this is time domain signal. In frequency domain, so it will have a spectrum like that. Okay, 1 by TB. This is the okay. Now this I want to spread this into something large like this. Large like this. 0. Okay. This is some large. This is equal to, say, let us say B. Is equal to original we can W, we can call it. This I would like to call it WSS. WSS, which is equal to 1 by TC. Okay. Now what is TC? I will show you. Now this is the original data we had. Corresponding spectrum was like this. I wanted to spread it like this. So for generating a waveform corresponding to this spectrum, what normally people do is a code. Use a certain type of a code. I will just, for your convenience, I am drawing. So let's assume that we are generating a code like 1110010. Again 1110010. This pattern is 1110010. This again repeats again and again. So this is one type of a code. I'll tell you about the property of this code later on. But this is one waveform. So this is called code. You generate one code like this, and multiply this code with this data. So you generate one code, you already have a data, but this duration, this is called, so this code has got a chip duration, this is called TC. So here each bit, this is called bit duration, each bit is of length TB, time TB, Here, this is called chip duration. So in one chip duration is called TC. So it is generated at a rate much higher than the bit rate. So here RB equal to 1 by TB. Here RC equal to 1 by TC. Okay, and RC is chosen to be much greater than RB. Okay, so this will be very small width. The code will have a very small width. Now, when you multiply this with this data, you will get say this is let us say d of t. This is c of t code, and x of t would be equal to d of t multiplied with c of t. Okay, what is that waveform? See, when this is multiplied with 1, same waveform will repeat like this. And this is minus 1. Suppose it is 1 plus 1 and this is minus 1. So this is also plus 1 minus 1. So when you multiply this waveform with that waveform, and then this waveform with this waveform, then what will happen? During this period, the same waveform will repeat. That means this will repeat like this. This will repeat like this, like that, like that. Whereas during this period, you are multiplying this code, and this code is repeating like this. So this code was repeating like this. During this period, when there is a 0, this is 1, 1, 0. So during 1, same code goes at the output. Another, this one, same code. When it is 0, it is minus 1. You are transmitting minus 1. So minus 1 multiplied by this code. So the reverse of this will take place. So instead of plus like this will take place. Like this will come. Okay, so that is what is going to happen. So this is the waveform that you will generate. So you will transmit. You need to transmit this data, but what you will do is you will multiply this d of t with the c of t and get x of t, which is like this, and the corresponding spectrum will be like this. Okay, if one looks at the spectrum, it is 1 by Tc. The maximum frequency is 1 by Tc. This is minus 1 by Tc. The minus WSS, you can call it. There it is minus W. Okay, minus W. So the spectrum, or in other words, the highest frequency in the spectrum, it depends upon the bit rate. Okay, RB. You can call this as RB. You can call this as RC. So we can call highest spectrum is RB here. Here the highest frequency is RB. Here the highest frequency is RC. So RC is much greater than RB. That is how we have selected. So RC is very much greater than RB. This is what we have selected. So the ratio of this. Let us call it as like this: RC by RB. In other words, TB by TC. This is called processing gain. So the amount of spread is this value. So we can always design a spread spectrum system by selecting a particular code in order to spread and ensuring the required amount of spread by selecting the rate at which you will generate the code, and then getting. This is called processing gain. The amount of spread that you will get is called processing gain because it provides some gain for you to mitigate the effect of jamming. So what we are doing is we have tried to understand spreading the spectrum. So you have data, corresponding spectrum is like this, and you should always remember that this is the energy in this spectrum, this and this area and that area both will be the same. Okay, so here now if you look at the corresponding waveform, it is like this. Now if you look at the corresponding waveform of this is very, very, very low energy spread over a large bandwidth. So very total energy spread in the one smaller bandwidth, so it will look high in this band. But if the same energy spread over a very large bandwidth, so it will look like a very small in amplitude and small look like a noise for any third person. Now for an intended person, now I want to transmit my signal to you, for example, one particular person. And you will know what I have done. You will know what kind of code I have selected, and you will use the same code to get back this spectrum from this spectrum. So you will what you will do? You will undo this process. You will multiply it into the same operation reverse way, and then get back the original. Whereas somebody who does not know enemy, for example, enemy will not know what is the code I am using. So they will not know how to get back the original message. So it is very difficult for the enemy to intercept my message. That is one thing. Another thing is that if the enemy has introduced some noise, or enemy introducing jamming, and jamming will be in this area, in this band, so that jammer signal will be always spread in the low strength, whereas the original signal can be enhanced. So let us understand this. So there is a need to survive communication in presence of hostile environment like jamming, intercept, and so on, which normally happens in the military communication. And for which a technique is required, that is called spread spectrum, we said. In which what we do is we will spread the original spectrum of the signal into a very large spectrum, and then we assume that will help us in reducing the effect of jamming. How do we spread the spectrum? That is using a code. You multiply the code with this data and then spread the spectrum, and we achieve this. This code also should have certain properties. Unless it has those properties, it will be difficult for us to get back the original signal. So we will try to understand that. So now, so far, what we have understood is that we can spread the spectrum using a code, which will be known only to the intended user, friendly user. It will not be known to the enemy user, and therefore we assume that the communication can survive in that kind of an environment. Okay. Now, one thing.